All right, hi everybody. Welcome back to section 7.3. And in this video, we're going to take a look at solving our first initial value problem using these first translation theorems and the inverse of it. So we're going to solve an initial value problem. What does that mean? Solve a differential equation, which is what this whole class is about. So we're given this second order differential equation, y double prime minus 6y prime plus 9y equals t squared e to the 3t, and we're given some initial conditions. Y of 0 equals 2 and y prime of 0 equals 17. Okay, so like we typically do for solving an initial value problem, which we learned in section 7.2, the first thing we want to do is Laplace transform this entire differential equation. So step one, we're going to Laplace transform. Okay, so this would be Laplacing both sides. We could do this. Laplace both sides. So y double prime minus 6y prime plus 9y equals a Laplace of t squared e to the 3t. Okay, so you've probably done a couple of these by now. So what we can do is just separate each of these terms, that linearity property. Also going to take out the constants, so -6 comes out, plus 9 times the Laplace of y prime, forgot that. Um, and equals the Laplace of t squared e to the 3t. Okay, so this right here on the right-hand side, t squared e to the 3t, before we learned the first translation theorem, this would have been quite a handful to solve using the regular Laplace transform definition, but we have the first translation theorem that will help us out. So let's come off to the side here and figure that out. So here I'll say like side. And the first translation theorem is Laplace e to the at times a function f of t equals Laplace of just that function f of t, and s is shifting a units. So that's our first translation theorem. Okay, so for this example here, the Laplace of t squared e to the 3t would equal the Laplace of t squared, and s shifting 3 units to the right. And the Laplace of t squared, we could see it to the table on the right, is just 2 over s to the third. So this is 2 over s cubed. And s is shifting 3 units to the right. So the Laplace would end up being s minus 3 cubed on the bottom. So that's where the first translation theorem comes into play for us. Okay, so it ends up being 2 over s minus 3 squared. So that's some side work. And then the rest of these, we know what they are, like Laplace of y double prime, Laplace of y prime, Laplace of y. It's all given here in the table if you're not remembering those automatically. So let's go ahead and write those down. So this would be um, s squared times f of s minus s times y naught minus y prime naught. I'm gonna put brackets here just to show like that's the double prime. And then minus 6 times s times f of s minus y naught plus 9 Laplace of y is just f of s by definition. And this is going to equal what we just found, 2 over s minus 3 squared. All right, so we know what y naught is and y prime naught is. We're given them as our initial conditions here. So this would be, or let's just go ahead and plug them in. So I would have s squared f of s minus 2s because y naught is just 2. Y prime naught is just 17. So minus 17 minus 6s times f of s. And y naught we already saw was 2. So this would be minus 6 times negative 2 is going to be plus 12 plus 9 f of s and equals 2 over s minus 3 squared. All right, so a couple things could combine. I have a negative 17, I have a 12, that becomes negative 5. So this ends up being s squared f of s minus 2s minus 5 minus 6s f of s plus 9 f of s equals 2 over s minus 3 squared. Okay, so that takes care of our first step, which is Laplace transforming. And so the second step, if you recall, when we do these initial value problems, is we want to isolate f of s. So we want to get f of s by itself and move everything over to the right side. So notice how these terms have f of s in common. So I'm going to factor out f of s from those terms. So this would be s squared minus 6s plus 9. I'm factoring out an f of s. And I just have that negative 2s minus 5 left over. And my right side is still the same. Okay, so I'm going to move over the negative 2s minus 5. So what I would have is um well, s squared minus 6s plus 9, that actually factors into s minus 3 squared. So that works out nicely. So I think we'll just take it that step. I was trying to um right take it step by step, but I think we can fast forward a bit. So s minus 3 squared is a new term, and so I have 2 over s minus 3 squared plus 2s plus 5. And now what I want to do is divide over that s minus 3 squared. So when I divide over that s minus 3 squared, what I would end up with is 2 over s minus 3 to the, excuse me, I was wondering why that was a little strange. we found that it was 2 over s minus 3 cubed, but I keep writing squared in the problem. So maybe you caught that, maybe you didn't. Sorry about that, but it should be cubed. That was throwing me off a bit. So go ahead and fix it to cubed if you were not writing that already. So when I divide by s minus 3 cubed squared to both sides, I end up with s minus 3 to the fifth plus 2s plus 5 over s minus 3 to the fifth, excuse me, squared. Okay, so this is what we're left with. Um, if you can recall that 2s plus 5 over s minus 3 squared, that is actually a problem we've seen before. So from example 2, in this 7.3 lecture series, using partial fraction decomposition, we found that 2s plus 5 over s minus 3 squared using partial fractions decomposition is 2 over s minus 3 plus 11 over s minus 3 squared. So using previous work from this lesson, this turns into 2 over s minus 3 to the fifth plus 2 over s minus 3 plus 11 over s minus 3 squared. Okay, so we have our f of s, and we do that because our last step is going to be inverse Laplacian. Okay, so the inverse Laplace of f of s is the inverse Laplace of these three terms. Okay, and by definition, the inverse Laplace of f of s is just going to be y. So if you're not remembering that, here's a table just in case. Like if you inverse Laplace f of s, what do you end up with? Just y. So we get y, which is what we want. We want, for a differential equation, like the goal is to get y equals some function, right? In terms of t. So that's our goal. So we have y equals, and we just got to figure out the rest and inverse Laplace these terms. So let's go ahead and separate them out. That always makes it easier. So inverse Laplace, I'm going to take the constants out. So this would be 2 times inverse Laplace of 1 over s minus 3 to the fifth, just to make it easier for what we need to if we need to manipulate anything or easy to recognize anything. I'm going to take out all these constants. Okay. So I this third term is okay. We don't really need to manipulate that at all. Same thing with 1 over s minus 3. But this first term, we need to manipulate that a bit. Okay, because I'm thinking, s to the fifth. And with s to the fifth, right, I'm looking here. I'm going to end up with something like t to the n, but I would need like a 4 factorial on top in order to come back in inverse Laplace. So what I need to do here is set up a little manipulation for us and have the inverse Laplace, and I'm going to write 4 factorial over 4 factorial on top. And these other two terms are fine. We don't need to do anything. I just know that this third term is going to be a first translation inverse theorem. Okay, so now I'm going to take out the 1 over 4 factorial. So I would have 2 over 4 factorial inverse Laplace of 4 factorial over s minus 3 to the fifth. Okay, so now we're in position to use the inverse first translation theorem. So inverse first translation theorem. And so you should have it handy while you're looking at these notes, but let's just recall it a bit just in case while we're in the process. So inverse Laplace, f of s. S is shifting specific units A. Well, that's just e to the AT, f of t. So y is going to equal 2 over 4 factorial. That ends up just being 1/12. But this is 4 or inverse Laplace of 4 factorial over s to the fifth. And where s is shifting 3 units to the right. Plus 2 inverse Laplace, 1 over s minus 3. We don't really need to do anything with that. We go down to our table. But yeah, that's just going to be our good friend right here. 1 over s minus a is just going to be e to the AT. So no manipulation there needed or translation at all. And then our third equate term, inverse Laplace. This would be 1 over s squared. And s is shifting 3 units to the right. Okay, so what does all this turn into? It turns into 1 over 12 t to the fourth e to the 3t plus 2e to the 3t, right? Because this one is easy. Just e to the AT and plus 11t e to the 3t. And that's our answer. Okay, so that's our first example of solving an initial value problem. It's the same idea where we, Laplace transform, isolate f of s so that we can inverse Laplace and end up with y. And so here's where we just have different situations where we need to use the first translation theorem or the inverse first translation theorem and shifting. Okay, so once again, this is an example where I'm going out in full detail. You do not need to go in full detail here. You can, if you identify steps, go ahead and take them. This is me just going over all the possible steps and rewriting the theorems and etc. So don't worry, it's not always as long as just me going over in specific detail. But thank you for watching. That takes care of the S-axis translation. We'll be covering the T-axis in the next set of videos, and then unit step function. But this is it for the first translation theorem. So thank you for watching, and I'll see you in the next video. Take care.